Okay, maybe we should get started. Shall we start?
Hey, we're gonna get started.
Um, so before the panel, we will have two talks. So next talk will from Professor Gigi Park, who is assistant professor in CSE at Michigan. So before joining Michigan, he was a postdoc researcher at Stanford, and before that, he was a PhD student at the University of Michigan, University of Washington, CS, supported by Apple AI and ML Fellowship. He did his undergrad at Caltech. Uh, Professor Park's major research interest lies in the intersection of computer vision and graphics, where he's the lead author of Deep SDF, which introduced neural implicit representation and made a substantial impact on 3D computer vision. And today he will be talking something slightly different. He'll be talking about diffusion PDE, generative PDE solving, and their pastoral observations. Without further ado, let's welcome Gigi.
All right. Thank you, Ching, so much for the nice introduction. So as Ching introduced, I'm an assistant professor here at UMichigan Computer Science and Engineering Department. And my primary research focus is on 3D and 4D reconstruction and generative model. But recently, I am more and more interested in scientific applications of these 3D or 4D or even like video type of diffusion models and generative models. And today, as the topic is about generative AI and their scientific applications, I'm going to be talking about our recent publication named DiffusionPDE, Generative PDE Solving Under Partial Observation. So this work is done with collaboration with some of the students in University of Michigan, including Jiahe and Jichen, and a postdoc from Stanford, which is Guangdao. So without further ado, I'm going to start. So today we're going to talk about solving differential equations. So let's talk a little bit about what are differential equations. So differential equations are basically tools to describe the laws of physics and is a cornerstone for physics and many scientific domains. So some of the examples of these differential equations are heat equations that are used to describe the motion of heat, the spreading of heats. So it's a pretty simple equations, as you can see here, that describes this motion of heat dissipations. Some other important applications of differential equation is Navier-Stokes, as a lot of you probably have already heard, that described the behavior of fluid. And using this seemingly simple equations, in differential equations, you can describe the behavior of a very complex fluid, which is pretty awesome. And the last equation that is being shown is the Maxwell equation that describes the relationship between electromagnetic field. And that is also very useful for a variety of applications in electronics, not to mention some of its applications for other big physical things like nuclear fusion to contain some of the plasma by controlling these magnetic fields. So you can see that differential equations are, it's a very important topic, and It's a cornerstone that describes many physical and scientific phenomena. Okay, and how do we solve these differential equations? You might think that because we have these equations, that's it, right? We just analytically solve and predict everything. And it's going to be very efficient. So one example of the case where this is possible is velocities, and some people call it ordinary differential equations. So here's an example. The velocity is described as the differential equations here, dr over dt. And you can accurately predict the position at any time t you want by simply doing an integral of that. And you have an analytical solution of what to expect at any time t of the position r. So this is great if you can solve all these differential equations analytically. You can just suddenly jump into the time and describe what's going to happen. However, these cases where there exist analytical solutions for these differential equations are actually quite rare. Some of the reasons are that these equations oftentimes cannot be even solved because they're too complex, or oftentimes the boundary conditions are non-analytical. Or this is very often the case that in computer science or any type of computing related scientific domains, there requires a discretization of variables. So oftentimes your observations are not described as a function, is just merely a samples in some discretized spaces like grids. And even if all these scenarios are not the case, it is oftentimes very computationally infeasible to analytically solve these differential equations. So it is the case that we most often need a numerical solvers to solve these complex differential equations. And these are usually iterative. You cannot just jump into the future and look into what it is. You need to iteratively solve it usually. And oftentimes it requires approximations and computationally expensive. Okay, so today let's talk about specifically about PDEs, which stands for partial differential equations. And let's talk about how to solve them numerically. So I'm going to give an example of this partial differential equations, which is the Poisson equation, which looks like this. So it's not very scary. So basically, you see that phi is a second derivative or second gradient of another function f, which you can write it as a Laplacian operator. So you define a Laplacian parameter operator f, and that's going to be your observation phi. And you can write it in a more detailed representation here that basically explains these Laplacian operator. So you're going to have the Laplacian phi, and you're going to have the original function f, and their relationships are written as a Poisson equation. So essentially, let's talk about an example here. So let's say you have a Laplacian period. You have a Laplacian of an image, okay, as shown here. And this is what we call phi, okay? So Laplacian of the image intensity, so we call it phi. And oftentimes the task in this numerical PDE solving is to find out the original signal f that gives rise to the observation of the derivative of f, which is phi. And our goal is to find this original image. And as you can see here, the relationship between f and phi are discrete because your observations are not an analytical function, it's rather an observation in the discrete sample space, which are grids. And there are a large number of variables, which is the number of pixels. And the boundary conditions oftentimes can be very complex. Okay, so one way of potentially solving this problem is doing a simple numerical optimization, as you probably all know about this. So the key idea is you want to optimize the f of x, which is the original intensity signal, so that this fx satisfies these constraints given as Laplacian of f is equal to phi. So you would use some methods that, for example, gradient descent in order to minimize this objective in order to solve for the pixel values of this fx. Well, this is a very simple method. Oftentimes, this simple numerical optimization method is not very accurate and oftentimes hard to optimize and could fall into local minimum. Building up on top of this very simple idea of numerical optimization, there has been a series of work that you might have already heard about, which is called physics-informed neural network. And the key idea is very, very similar. So instead of optimizing the grid of pixels, why don't we represent these original signal, f, as a neural network? So essentially what it does is that it keeps a neural network, you call it U here, and you can query and position in this neural network with a coordinate x, and that gives you the output of these fx, basically, the original signal. And you can optimize this neural network so that this neural network satisfies all the PDE constraints given for you. Okay, so given a PDE function, fx equals 0, for example, then and then you can solve for this, you can optimize this neural network U such that all of these constraints are satisfied. So this is analogous to just naively optimizing for the pixel values of your original signal, but is instead represented as a neural network. It's very simple and oftentimes effective, but as you can see, you need to optimize the entire neural network for a single scene, so it's very slow and oftentimes less accurate and hard to optimize, and thus fall into local minimum. Perhaps a better received way of solving this is a finite element method, which formulate these PDE solving as a large linear system, such just AX equals B. Here, A matrix is just formulated as some discrete Laplacian kernels. So something looks like this. And then fx is simply the pixels. You just flatten it and make it as pixels and make it a vector. And Laplacian of f is the observations you have in the Laplacian space. So using this pretty simple system, you have a really, really large linear system where the matrix A is the dimension of matrix A is equal to number of pixels by number of pixels, which is huge. This is really popular method and is a cornerstone of many of these PDE solving methods, modern PDE solving methods. And these are very accurate, but as you can see, it can be very expensive because it's solving large linear systems. So in order to avoid solving these large linear systems and avoid this time complexity, what people have been trying in the literature is using neural network to find a shortcut. Okay, so the key idea is to find a direct mapping from some observation space to a solution space. A famous works here is called Fourier neural operator and deep ONet that finds the mapping from the Fourier space of the input and the Fourier space of the output. If you apply that to our story, then what happens is that I'm giving you this Laplacian image, and you simply train a network that maps this Laplacian image into the original signal without worrying about solving this system analytically or numerically. So given that we have gone through all these prior methods, let's try to define our goal before we get into the method itself. So the goal is that we want to solve a forward and backward inverse PDE solutions. So we want to compute the solution or the final state of a partial differential equations given some parameters or observations. Okay, and oftentimes people classify these equations into two systems. The one is a static systems, such as these 2D Darcy flow that does not have any time component to it. So an example of this case where you have this coefficients shown in the left side. So you can understand this coefficient as something like material properties of of a metal or something, and the solution space will be how the heat will be, how the temperature will be, So these are static systems, and there are dynamic systems such as Navier-Stokes. It obviously involves time components. So what you want to do is you want to predict the state of the system at time t given an input which is at time 0. Okay, and you can solve this for PDE using all of the previous methods that I talked about. So these are the current state of the art for the literature. And here's some example of the visualization of Navier-Stokes. So this is a velocity field that you, given the initial state, you want to predict how this fluid will evolve in the future. Okay, so inverse PDE solution is exactly the opposite of that. So for example, we're given a solution. So this is our observation space, and we want to infer what is the coefficient that gives rise to this solution. And for the case of the dynamic PDE, we're given the final state of the scene, and then we want to find what was the initial state that gives rise to this final state. Okay, and one way of doing this is that if I give you a forward model, then you can use this forward model differentiably to optimize the initial state to fit to the final state. That is one method. And yeah, as I briefly went over in the previous slides, there exist numerous forward and inverse methods in the literature. Okay. Despite the fact that there are so many methods in the literature, there exists a significant gap, which is that the partial observation nature of real-world signals. So existing methods, most of them, are designed to handle full observations. They assume that they have full observation either of the initial state or the final state. And hence, they cannot deal with sparse initial or coefficient observations. Well, this is a pity because most real-world observations are sparse. And if you have to deal with them, you're kind of stuck because most of the existing methods just cannot handle them. So I'll give you one example where there are partial observations of the real-world scenarios. So imagine trying to check if the maximum velocity of this system, so it goes from initial to final state, so this is a fluid going. So you want to check if the maximum velocity at anywhere and any time of this system is above some certain threshold, right? And if it's above the threshold, that is a problem, right? So you want to detect this as a problem, okay? Well, how would you do it? You will probably, install some sensors and try to get the initial state and then solve for the final state using existing finite element method or neural operator, whatever that is. But you immediately hit the wall because you immediately find out that you're not given the full state of the initial state. Rather, you would have a sparse observation of the initial state, which is shown in the left side. So we're kind of stuck here because we can only install a certain number of sensors in the scene, because if you try to install so many sensors, that will eventually interact with the scene itself. So there's only so much sensor you can install, so you cannot simulate from the full initial state, and hence cannot use existing methods. You can also see from another example when you try to simulate the full state of the this fluid dynamics where the airplane is flying, you cannot afford to install sensors everywhere on the surface of the airplane. Okay, so I hope I was successful in persuading you that we need to incorporate the sparse observation aspect when trying to solve PDEs. And thus, we need to simultaneously fill in these missing observations and solve the equations, which is a problem that wasn't being explored too much. And ideally, we hope these systems to be flexible so that we can have one model that can do both forward and inverse PDE solving, right? And we hope that this model can accommodate observations that captured from anywhere and anytime. So we propose a generative PDE solving method that we call DiffusionPDE, using diffusion model, as the name suggests, that trying to match this criteria shown above. The key idea is that we model the joint distribution of two spaces that we're going to talk about briefly. And we use a guidance techniques that's well known in the diffusion model community to enforce various constraints. And we claim that we can solve both forward and inverse PDE using one model using this method. Okay, so in DiffusionPDE, as I said before, we try to model the joint distribution of two spaces. And what are these two spaces? For the static PDEs, that will be the coefficient and the solution spaces, right? So that's what's shown here in this diagram. And for dynamic PDEs, these joint distributions will model the initial state and the final state simultaneously. So this model is trained on trained with diffusion model algorithm to be able to generate a joint image, concatenated image of these two distributions and concatenated on the channel dimensions. And during inference, we use various guidance techniques in order to sample from this joint distribution, at the same time trying to respect the partial observation that we have at our hands, and also try to apply a PDE guidance in order to guarantee, or at least try to make sure that your output respects the physical constraints described by the partial differential equations. Okay, so this phase, different from the regular unconditional diffusion samples, we guide this denoising process with our sparse observations and known PDE equations. Okay, so here's another review, probably like fifth review of diffusion model you've seen today. So these diffusion models, I'm going to go very quickly. It learns score function. It just tells you the best way to improve the realism given a corrupt image. So the backward of this diffusion model is a denoising process. It's what's important, that you learned this score function that tells you how do I improve this image to look more realistic according to the data distribution. Okay? And the question is now, what if you have a partial observation shown as y here, that you want to make sure that your output fits to this y? So you want to know that okay, you have some pixels that you know the values, and how do I denoise the process in such a way that the output values matches this partial observations? Here we use this technique called diffusion posterior prior, where we add these partial observations into the equation and modify the score function to accommodate these partial observations, and we call it guidance. Okay. So the idea is essentially to learn the probability, the gradient of the probability, log probability of the posterior function, that we have x given y, the partial observations. And we can simply get this by adding some components to the original score function. So this is the score function trained with the diffusion model. And another loss, we have observation loss. These are coming from the sparse observation that we have. And the final term is the PDE loss that tells us, okay, these two spaces that we're modeling should satisfy the equation that we have in our hand. Okay, and that can be further, massaged into this equation with observation loss and PDE loss. I won't go into too much details for this. If you're interested, please check our publication. And this is the final state, okay? So we apply guidance in the denoising process in order to accommodate this observation and PDE losses. And this is the whole picture. Okay, so I hope it was clear how this algorithm works. Okay, so let's move on to the result. So our main result shows that our diffusion PDE performs significantly better than prior state-of-the-arts in solving both forward and inverse problems under sparse observations. And this is to say that these existing methods, most of them are deep learning based methods, are not really designed to accommodate for these sparse observations. Rather, they assume that their either initial or final states are fully observed. And it is also to note that most of these methods have a special model for either forward or inverse problems, but our diffusion PDE can go through any one training process and can be applied for both forward and inverse PDE solving. Here's some quantitative results. So as you can see, this is the partial observations, and these are results using PDEs and then PDE losses and also the observation losses. And different columns shows that whether they use the both coefficients and the solution partial observations, or they use one of the either one of these partial observations. And you can see the error is very low. And here's a video that shows you these denoising process. So in the prediction column, we visualize the clean image prediction of this diffusion model as time progresses in the denoising process. So it starts from some random guesses and it denoise it with the guidance, and it keeps getting closer to the observations and the PDE constraints, as you can see here. And the only observations we're having is the partial observation on the coefficient side. We have no observation on the solution side. Yeah, so as I said before, you can recover both of these spaces simultaneously with sparse observation at any side. And you can see for both forward and inverse problem solving, you can see that diffusion PDE performs much better than existing state-of-the-art for the same task. Here's some results on Navier-Stokes for both forward and inverse problems. So as before, we're giving either the sparse observation on the initial or the final state, and we're trying to predict the final or the initial state, shown as a different rows. And you can see that the existing methods, they just sort of completely fail to do this because they're not designed for this task. And as before, this is a video of the denoising process. And as before, the prediction columns shows the development of clean image prediction. And in this case, we're giving the observation in the final state. So it's an inverse problem of the PDE solving. In this result, what we show is a similar problem, but here we have obstacles in this fluid simulation, and we randomly sample the locations of these obstacles, so it makes it a harder problem because the boundary condition is more complex. And as you can see here, we're given the partial observation of the final state, which is only 1% of the pixels randomly selected from the final state. And using our method, we can solve for the initial state that gives rise to the final state. And compared to the ground truth, we're much better than the state of the art for doing the same task. Okay, here I think is another interesting experiment. So here, instead of having a partial observation simply on the spatial side, we assume to solve a 1D PDE that has a time component to it. Okay, so in this case, the y-axis is time, and x-axis is the solution space, and we have only very, very sparse observation across time. So this is a scenario where we installed 5 sensors in the scene in a one-dimensional world, and then we let this sensor read their signals across time. Okay, so hence we have these lines. These are sensor outputs. And just from these extremely sparse sensor readings, our diffusion PDE is able to recover, and in this case we call it reconstruct almost pretty accurate, almost perfectly accurate reconstruction of the ground truth, which if you compare against the other methods, it's not very good. The one exception is the PINN, the physically inferred neural network method that I briefly mentioned before, which is actually suitable for this case in terms of its formulation, because it involves simply an optimization of the neural network to fit this partial observation, and it uses its innate inductive bias of the neural network to fill in the details of the remaining spatial coordinates. But you can see here it does pretty good job at reconstructing the ground truth, but is not as accurate as our diffusion PDE. And I'm gonna for the rest of the slides, I'm gonna show some additional analysis of the diffusion PDE algorithm. So we realized that the diffusion PDE is robust to random noise on the sparse observation. So if you add noises to these sensor readings of the sparse observations, we can see that it's pretty robust. And it can also is robust to the, I don't know what's going on. Okay, yeah. Oh. Yeah, the connection seems weird. Okay, yeah. Anyway, so this diffusion PDEs is robust to different sampling patterns. And because it's a generative model, it is able to suggest multiple plausible solutions given the same observation. So as you can see here, we're given just half of the scenes and sampled 500 random points from the left half side and try to recover that with different seeds, which gives you a very different results of how to complete the right side of the scene. And then we also compared against some easy target, which is just train a unit, as I suggested in the earlier of the presentation, that goes from the initial state to the final state. And if you don't use the diffusion PDE and rather use just a simple UNet, it doesn't perform as well. And here, what we're showing is that we're trying to compare I don't know. All right. Yeah, so we're trying to compare whether these PDE loss actually helps, because if you remember, we have the observation loss and the PDE loss. And as you can see here, this is the error map that shows with both PDE and the observation guidance. The left is the one that only has the observation guidance, and you can see that the PDE loss actually really helps in reducing the error. And this is another comparison against a baseline that if you have a forward function, as I say, you can use it for a inverse problem. And this is a result showing that DiffusionPDE performs much better. And this is a baseline that shows that if you complete the partial observation using a simple radial basis function, and then use the existing method to do the forward process, you can see that it doesn't work at all. So another data they want to show is that DiffusionPDE is excellent for solving PDE given partial observation. But what happens if I give a full observation and try to compare the performance? The result, as shown here, is that DiffusionPDE is almost as good as the state-of-the-art method that assumes full observation. So it can be used for not only partial observations, but of the cases where you have the full observation, and it will work competitively against the competitors. Okay, so today I presented DiffusionPDE, which is a generative framework for solving partial differential equations from partial observations. But it is not without its limitations. So DiffusionPDE is currently limited solving only slices of dynamic 2D PDEs, meaning that we're only modeling the joint distribution of the U0 and UT for Navier-Stokes, for example. And we'd like to extend its capability to recover the full time intervals, the all intermediate stages between 0 and t, instead of just modeling the initial and final state. And we also want to extend this framework to higher dimensional solution spaces such as 3D or 4D. And finally, we want to note that our framework is not as fast as other state-of-the-art methods, such as FNO, or the Fourier neural operator, that just involves a forward pass of a neural network. And our method will suffer from a slowing sampling procedure and would not be suitable for cases where you need a faster solution, such as the real-time applications. Thank you, and I'm happy to answer any questions. Yeah.
Yeah, very fantastic talk, JJ. Greatly appreciate it. Yes, I think it's very interesting to see how this can use to solve a PDE. And you mentioned the joint distribution on two space, right? And by the joint distribution, do you mean like you train the diffusion separately on each of the space? Or are you training them together? For example, if you're using the same noise to generate data on both ends, or they're just separately? You depends on or rely on the PDE function.
Yeah. That's a great question. So over the entire world, we just have one model that does everything. So we have a joint space of the initial and final state. We just concatenate them and make it as like a single image with larger channel size and just model the distribution of that concatenated image.
I see.
Yeah.
And this kind of the pair data is also unique. So you always have like the pair data for each time.
Right. You need a pair data. For example, for Navier-Stokes, you need a pair data of the initial state and the final state.
And they are also one-to-one mapping. So with the same like one sample, it will not be the other.
Yes, but I think theoretically there could be some stochasticity if you're trying to solve a stochastic PDE. But yeah, but for our case, I think it's mostly just deterministic mapping. So we have fixed pair between initial and final state.
Yes, and also for the PD kind of representation, so if we're using like the DPS to constrain on this, do you think that will be for sure guarantee the PD equation will be satisfied in your solution?
That's a good question. Not always. So there are always some residuals that even if you have these losses, the PDE losses, you still have some residuals. That means that the PDE constraints are not perfectly satisfied. And that's a great point because it's a weakness of existing optimization-based methods like PINN that just simply optimize it, and its residual is always not zero. It's never zero. Yeah.
Okay, cool. Thank you.
Yeah, thanks.
So can you fine-tune your model to solve different type of PDs? Like say you train on one type and then you can fine-tune.
We haven't tried it, but I think people are working on some like foundation models for PDEs. So that would be an interesting direction for research.
Okay.
Yeah, yeah.
Okay, let's thank PD again.
Oh, yeah, we can talk later. Yeah, thanks.